So you should have just learned about how to use Newton's third law and how you can use it to set up equal and opposite forces. This is a classic problem that I'm about to do, often called an Atwood problem, which is something involving this pulley and then masses hanging from it. So I have this Atwood problem where I want to find the acceleration of my system and the tension acting on each of these objects. So to set that up, the first thing that we need to do, and you guys need to definitely have this as a habit, is to draw the free body diagrams for each object. I'll do this object on the left with this one here, and I'm going to draw a vector that's 2 units long to represent the 2mg force of gravity acting on it. Over on this one here, I'm going to draw one that's only 1 long, representing the mg that's half of that, because we know that that's how the weights exist on each one of those. Then they have tensions on here. And if I'm being careful with my tensions, my vectors, I should try and draw them with appropriate lengths. So I need to think about what direction the system is going to accelerate. It's going to accelerate so that the 2m is going to fall faster and faster, and the m is going to start moving up and move faster and faster. Which means if I'm drawing this, I need a vector here that starts moving it upwards. There's my tension on the m. And I need something here that allows it to be moving downwards. So I did these both at 1.5 because that means that this one has a net upwards force and this one has a net downwards force, just like we predicted. So there's my free body diagrams. And I'm going to try and set up some of our forces equations. But the minute that I start trying to do that, I'm going to run into an issue. The issue I'm going to run into is if I try to say up is positive and down is negative, then I'm going to say 2mg and mg are both pulling the same direction. But they're really not in this system. This is really a system where we have a tug of war between the 2mg and the mg. So we're going to need actually a new type of coordinate system that isn't just based off of a coordinate plane that says up or down is at positive or left or right are positive. Instead, we're going to set up what I call a coordinate of motion, something that describes the direction that all of the objects are moving and says we're going to call this direction positive and anything going counter to that direction negative. So my coordinate of motion goes like this. It's going up on the right side and down on the left side. And I'm going to define anything going in this direction, which I guess is counterclockwise, I'm going to call positive, and anything that goes the opposite direction negative as I set up these forces in my net force equation. So going through this net force equation, I'll start with my first force, that my one that's like furthest in my bottom left, and that's going to be a positive force because it's going down in the clockwise direction. It's the direction that I predicted my motion would be. Then going against that, I have, oh, this should say actually 2m because it's the tension on the 2m. This is the tension on the 2m. It's negative because it's going the opposite way. Then I have my m right here, my tm, that's going in my positive direction. So that's going to be positive tm. And then minus mg. And we don't know what this equals. We don't think that this is an equilibrium. We have no reason to think that. In fact, it's asking about the acceleration, so it's probably not an equilibrium. So we can't say we know what this equals. Instead, we're going to have to do the math here. But before we can really do much, these two we could combine. We could just do 2mg minus mg and turn that into mg. It's 2mg minus mg equals mg. But what do we do with these two? Well, we remember that these are actually an action-reaction pair. I have the 2m pulling on the m, and I have the m pulling on the 2m. That's an action-reaction pair from Newton's third law, which means they have to be equal and opposite in direction, and they cancel. I knew that already. That's why I drew them as the same length. But now we've proven it using Newton's third law. So we know that the sum of our forces is actually, sum of our forces is actually equal to mg, which means we can set up an acceleration equation because the acceleration is the sum of the forces over m, and the sum of our forces is mg. But I did a sum of the forces for the entire system, which means I need the mass of the entire system. And the entire system has a mass of 3m, which simplifies down to g over 3 for my acceleration. You always need to, when you're doing these problems, find acceleration of the system first. When we do the whole system, we can disregard these um, tensions that we don't know values of because they just cancel out because they're equal and opposite. But now that I know the acceleration of the system is this, I can now find the tension in the system by just picking one of the objects. I'm going to pick this object here because it's actually a little bit more convenient because it's only one mass. And I'm going to say this system has an acceleration equal to the sum of the forces over m, but the acceleration is g over 3 because we already found out that the system's accelerating g over 3, which means this has to be accelerating g over 3. Otherwise, the ropes stretch or break or something. Um, then the sum of our forces acting on it, well, it has Tm in the positive direction, because I said up stuff going this way is positive, minus mg all over m, because the mass of this object is just m. So I can multiply both sides by m. That gets me mg over 3 equals Tm minus mg. I would then add mg to both sides, plus mg, and that gives me, that's really 4/3. Tm equals 4/3 mg, because that would be adding mg is the same thing as adding 3 mg over 3. So 3 plus 1 is 4. So there's the tension mg, or a tension for m. I can actually prove that this has the exact same tension. I'll have to do it a little bit smaller though, just because I'm running out of space. So again, the acceleration of this object would be g over 3. And then it's going to have 2mg minus T2m all over a mass of 2m. So then I get 2mg over 3 equals 2mg minus T2m. And if I add this to both sides and subtract that, so I'm going to add that and subtract that, I end up getting T2m also equals 4/3 mg. And we would expect that to happen because we said that they were equal and opposite forces, but now mathematically we've also proved that's the case, as long as it's accelerating at based on this acceleration that we have. So that's how you do an Atwood's problem. That's some of the applications of Newton's third law. I hope this helps you guys out as we do some example problems going forward. Thank you very much.